Hi, my name is Tao from Google. So today I'm going to talk about the open source RISC-V verification, process verification platform. So this is the agenda today. I'll start with introducing the RISCV-DV. It's an open source RISC-V instruction generator built on top of System Verilog and UVM. The next thing I'll talk about the end-to-end flow we built up to enable you do the code simulation with instruction simulator and the design. And we'll have a case study about how we actually apply this to actual processor verification, which is Ibex core. And we're also talking about the roadmap. We have a lot of interesting ideas we want to push forward this year. So I think last year on this stage, we announced that we are doing this kind of thing. We are building a System Verilog UVM-based kind of instruction generator for RISC-V verification. So we made it open sourced on this link. So you can actually download and give a shot. So before I dive into details about what we do since we released, I want to just give you some background about this solution. So set on background so you know what we are doing. So basically, this is a System Verilog UVM-based instruction generator. So it generates a whole program, including a highly stressful dynamic instructions to test your processor. And if you have a page table, if you support virtual address translation will also generate page table for you and also enable a lot of exception in the page tables. And also because we are going to test all the interrupt exceptions, we also generate the trap handlers for you to handle different type of interrupt, how to recover from the interrupt or recover from the exceptions. And also there will be data pages, stacks. In a sense that it's a complete assembly program. You can actually compile and run with your processor. So we made it open source January this year. So at the time we released, you support 32-bit IMC and also 64-bits of that. And we also support machine mode, supervisor mode, and user mode, virtual address translation, a regression suite, and also we support, because this is kind of System Verilog UVM-based solutions, we have to run with some commercial simulator. So we support, at that time, we support VCS and Incisive, which is from Cadence and Synopsys. And also on the ISS side, we support Spike. So, and we also delivered a very simple simulation flow, which is a kind of bash-based, very simple thing. So since release, we actually get a lot of feedback and feature requests. And so that drives us to deliver more since release. So on the right is kind of a set of things we added over the last year. So we added floating point, double position, and atomic extensions. And we add debug mode support, whatever relevant to processor verification. And also we add actually a functional coverage model to tell you what you have verified. And there are other things like hint, illegal instructions, and the handshake mechanism. And so there are a lot of things. So actually a lot of things are actually driven by the user request. It's actually a way that we feel that the power of open source help us to make it better. I will take next few slides to give you some more details about some of the major features we added. So the one on the left is illegal hint instruction support, which turned out to be a big hole in most of verification solutions because you can imagine that you generate a program, a legal program to compile and run, but you cannot actually generate a legal program to compile because the compiler doesn't like it. So we have a way to kind of mix illegal and hint instruction in the stream, so you can actually simulate that. So there are many different types of illegal instructions, like you can use reserve opcode, you can use unsupported instructions, also you can do CSR access to some CSR doesn't implement, also you can do like from the user mode, access machine mode register or vice versa. So there's a security problem as well. So on the right side is actually from the user that they are saying that, yeah, we have a lot of memories, internal and external memories. So we want to test that, okay, we want to kind of do the load store from different memory locations. So to achieve that, we actually have, in the generated program, we allow you to kind of link different memory regions to different places to match your memory map, so that if you want to test, you have internal memories, you have a PMP features, and also maybe you have a page table that's kind of saying, you can actually configure the generator to match the memory map of your design or your system. So the next thing is the debug mode support. So debug mode is kind of, there are some relevant features in the processor side. So in terms of verification, we generated, if you enable that test, we will generate a debug room in the memory so that when you can actually, in your test bed, you can send debug requests to your core, then this kind of a debug room will handle all the debug handshake or whatever things for you. So there's actually a lot of things we can test with the debug mode because you can do the e-break with the DCSR enabled or not. You can enter debug mode from external requests. You can do single stepping. You can have exceptions in your debug room. So there's a kind of a large verification space we need to explore. So one of the questions is that how do you know that the processor is doing the right thing? Because if you think about how we do the kind of cost simulation, because we take the spike or whatever simulator, ISS simulator, so you cannot actually send debug request to the ISS at the same time as design, because the simulator was finished simulation in 0 time pretty much. So how do you actually know that processor actually get into the debug mode, save the right context, and come back from the debug mode? So this is actually the question I got from the last summit, how do you actually do that? So in order to achieve that, we developed a kind of handshake mechanism to do that. So what I mean by handshake is that we kind of build in some programs in our whole program. Let's say when you go into the debug mode, you actually write out something to some kind of predefined address. Let's say once I get into debug mode, I say I'm in debug mode. I write to that address with some, you can see on the left, is some command or some opcode, whatever we define, to say I'm in debug mode. Then the next thing you can write is that what's the status of the debug register. So that's something you want to check. So once you have this mechanism, you can, in your test bench, generate debug requests, and you know what to expect. You expect the code to get into the debug mode. You expect the code to save some context in the debuggable register. Then you can actually wait for the program to run and write that thing back. So you can wait for the memory access to that address. Then you know the things are actually happening. So we use this approach to verify a lot of things, like the debug mode is one example. Interrupt is another example, because you cannot interrupt the instruction simulator at the same time as the design. And also, there are some memory access fault, so you cannot, so you basically generate the fault from your test bench, but you cannot generate the fault from your instruction simulator. So we do this kind of thing, so the program can generate something, then you can wait in your test bench to know the design is actually doing the right thing. So this is a functional coverage model I'm talking about. So this is actually very important. We are doing constrained random verification. Basically, you are generating a lot of random instructions. And how do you know you have covered the thing you care about? So functional coverage is actually an obvious answer. So you have to get functional coverage to tell you you cover all the kind of interesting corner cases you care about. So when we build this flow, we have many options. Like you can get something, you can have some probing to the design pipeline, or you can, some design has tracer, then you can give you some information, you can collect functional coverage on the tracer. But the problem is that we don't have standard tracer implementation across the open source processors. Some processors don't even have a tracer. So in order to kind of build a very general solution, we actually bypass the processor, RTO processor completely. So in a sense that we run our simulation with ISS simulator, then you can actually get the trace. The trace will tell you what has happened. So what kind of hazard condition, what different combination of the instruction has happened. So we can actually convert that in kind of a CSV format we define, then you can collect functional coverage on top of that. So there are a few advantages of doing this. The first thing is that you can see that this flow doesn't tie to our instruction generation flow, meaning that as long as you have your tests running and run with your instruction simulator, you generate a trace file, you can use this flow. You don't have to use our instruction generator. You can have your own generator. The second thing is that it's totally independent of RTO implementation. Even you don't have a tracer, you can use this flow. The third thing is that it's actually fast. I'll talk about the speed a little bit later, so why this kind of matters. And another thing is that it's very flexible to support different kind of ISS, because we make it like, we have a standard format in the middle, so it's just a kind of small script to kind of convert your log file, instruction log file to a standard trace file, then we can do the coverage from that. So this is actually the list of the functional coverage we have put in place at this point. Like you cover all the different possible operands of each instructions. Hazard conditions is also important. Corner cases for each instruction, underflow, overflow, divide by zero, this type of thing. Online memory access. And you have different operand values and branches back and forth. And if you have a branch prediction logic, you care about different branch history, whether you hit, or miss-hit, different combinations. And hidden instruction, illegal instructions, and some privilegeable CSRs. So this is a very generic approach, and you can actually use it with your own test generator without having to hooking up the RTO with our flow. This slide is about performance of the generator, which is important. At the time we released the generator, to generate a test with 10,000 or 20,000 instructions, it takes 30 seconds, something like that. It's not that bad, but definitely there's a lot of space to improve. So it turns out constraint random is not a free lunch. It's kind of, you need to take a lot of time to kind of optimize how you do the constraint random to make it fast. So we have done a lot of refactoring, so there's not a lot of technical details of how we do that, but eventually we actually improve the speed by 5 times. So we're actually doing another round of refactoring to even cut the simulation time by half. So apart from that, you can imagine if you have a big kind of complex processor, you might want to run a lot of tests. So we actually the flow has enabled you to kind of run everything in parallel. And if you have one test, like 100 iterations, we can actually further break down to different small batches. So you kind of parallelize and you can run it if you have enough machine, you can run it in a very short time. So that's how we actually improve the performance of the generator. So next, I'm going to talk about the flow. So the previous slides are talking about the generator itself. But the generator itself is not enough for a verification platform. So this is the flow chart for our flow. So I would just go from left to the right. So on the left is actually, you're starting from your generation. You have the source code of a generator. You compile it with CS, whatever simulator. Then you get the binary. Then you compile with the compiler, whatever, GCC or LLVM compiler. Then you get the binary. Then you run the simulation with your RTO processor and run with ISS. Then you get a log. So the key things in this flow is that I mentioned about the YAML-based flow, which means you can see at different steps, you have some input. Like when you compile the generator, there's a simulator's YAML, which will give you a specification of the command. When you run with VCS, when you run with different simulator, we actually abstract that part out of the flow. And also, when you run ISS, there are so many open source ISS in the RISC-V world. How do we actually make it simple to support different ISS? So I will show you some example of how the YAML file looks like. So this is the 2 YAML file we have. On the left is ISS YAML. So you can see there are actually 3 entries. One is Spike. So the other one is OVP Sim from Impulse. And the third one is Whisper from Western Digital. And you can see that it's just a kind of bunch of entries in the file. You configure how to run your test and kind of a bunch of kind of a variable you pass to that file. Then you can actually switch between different ISS. And on the right is like a test list because we want to support some regression flow. Then you have a regression speed. Like I said, you can run with different iterations, go in parallel. So it actually specify the regression. So this slide tells you some command lines. So you can see the first one, you run with simulator VCS. Then you run with VCS. If you have a different simulator on your local, you can run with Incisive, DSIM, Mentor Graphics Simulator. So it's pretty simple. And the second line shows you how to run with different ISS. Like say you have 2 ISS set up, one is Spike, one in Paris OVP Sim. You can actually pass both of them to the flow. What the flow will do is that you're going to run the simulation with both ISS and compare the result. What this gives to you is that you can actually, when you are developing your test, you don't have to run with RTO simulator. You can actually run with 2 ISS at the same time and get result. So it makes the thing much, much faster. So, and there are other examples that you can specify the target. Let's say, because the RISC-V is very configurable, extendable, so you can have different variations. So you can say, I run with 64 bits IMC or 32 bits or different variations. The flow actually make it very simple for you to kind of just say, this is the target, and just run it for me. So the reason we make things like this, rather than just support one ISS, one simulator, is that we want to build an ecosystem for the verification. So make all the extension easier. So right now, we support, on the RTO simulator side, we support the simulator from Synopsys, Cadence, Mentor, all the mainstream, and we also support metrics DSIM. And on the ISS side, we support Spike, Impulse, OVP Sim, and the Swerve ISS from Western Digital, and the Cell RISC-V model. So it's actually take me like one day of work to actually add in another kind of ISS or adding another RTO simulator. So if you want to use it and you have your own simulator, you shouldn't be too hard to do it. And on the right side, there's some predefined target. It's just I mentioned the different variants of the RISC-V. So this is a case study I want to go through. So we actually apply this to Ibex core. So Ibex core is the core from no risk. It's kind of 2 stages, RV 32-bit IMC, and it has a debug mode and the PMP support. So we're actually working pretty closely with the no risk team to do the verification. So the core is actually from zero RISC-V originally, and then there's a lot of new features added along the way. So this picture shows the actually end-to-end simulation flow. So compared with previous flow, it's actually have a real RTO. So you can see the red box is Ibex core. So we actually generate the program, load the program to the memory model of the test bench. Then we run both. Then again, we can compare the CSV. So it's actually pretty simple and standard flow. So here's the list of bugs we found in Ibex core. So one thing I want to mention is that Ibex is actually under very active development. So we expect to find some bugs. Some features is actually new. So you can see we found a lot of things in illegal and hidden instructions, which kind of expose the weakness of a common verification approach that we don't verify too much. We actually find bugs in Spike in this area as well. And debug mode is another thing, because we don't actually have a good way to verify the debug mode in the past. And memory access fault, interrupt is the main thing. We don't find too many bugs in the pipelines because the pipeline is relatively simple and the AOU has been used many times. So there's less bugs in that area, but you can see the distribution. Based on the bug, you can see what kind of a verification area we are focusing on and what we can do with this approach. Okay, the next thing is the roadmap. I think we are committed to make it better. So there are a few things, mainly 3 things we want to talk about that we are going to do in the future. The first thing is that we want to make a complete RISC-V verification platform, which means we need to support all the verified ISA. So we are going to add vector extension, bit manipulation extension next year. And we are going to kind of also on the coverage part, we are going to make the functional model, coverage model more complete to support more interesting cases. Basically, functional model is kind of how you, after you read the spec, what do you think is interesting from the spec? You make sure you cover it. Even you don't use the instruction generator, you have your own test flow, you can still sign off your verification with this coverage model to make sure you actually test the interesting scenario. We actually work with a compliance group, so you can actually run the compliance test with this as well. So you can actually see how compliance tests cover different things in the spec. So verification is not just the instruction generator itself. So we want to make it like kind of a full reference test bench to make sure, because test bench itself is similar. So we want to make sure we have an infrastructure set up so you can actually reference the test bench to make the adoption much easier. Like 1 day of work, you can actually get your processor hooked up and up and running. So this is on the verification platform side. So the next thing is kind of interesting. So you never know when you go into open source something different will happen. So when I open source this thing and somebody come to me and say, hey, we apply machine learning on top of your methodology and getting better result. I think, yeah, that's reasonable because you can do something to bias something. So, but at that time, when I look at the paper, I see, this is the way they did it. They're kind of hard because they kind of hack into my code and do a lot of things, which is not really good. So we are going to make this thing friendly for this kind of research, meaning that we are going to so I think machine learning can resolve a lot of problems in the verification world. One of the problems is that when you're doing constraint random verification, you might just running the same thing again and again and again, and there are some corner cases you cannot cover forever. So one of the problems machine learning world is trying to solve is that how do you converge your coverage faster by changing something in your test bench. So in order to do that, we want to make the generator more friendly in terms of controllability. We give you a lot of knobs you can control, then you can train your model to converge faster. The second thing is that we need to enhance the coverage model to provide different kind of more differentiation. What I mean by this is that you need to present a good problem to solve, because if the randomization, the coverage model is too simple, then you can pretty much get it build purely random. So we want to make it problem kind of harder so you can actually benchmark and see how your way can actually get the coverage convergence faster. So we are going to provide the APIs for the machine learning models so that you can actually provide the way to manipulate our generator, and we give you the way about the reward you get, how much more coverage you get out of that. So that's something eventually you want this platform to be used, apart from the RISC-V verification, to be the benchmark of different ML models. So that's our another goal. So the last page is the config. So RISC-V is very configurable. So we have many different ways to config. So you need to configure your generator to generate the thing that match your design spec. Then we have IIS. IIS is also configurable. So you also want to configure the IIS to match your design, so that you can simulate in the same way. And we have a compliance test. If you have something not implemented, you should not run the compliance test for that. We have the coverage model, also tied to some sort of configuration. If you don't support that, we should not generate in the coverage model. So all this type of thing need configurations. And we don't want to do in 5 different ways. So that's why we are trying to build a common way so that you just specify one config file. You can configure your instruction generator, ISS, compliance test, coverage model, and more things. So that's another thing we want to push forward on this thing. So one last thing I want to mention before I end the presentation is that we actually are going to move this development work from Google repository to Chip Alliance very soon. So we are kind of trying to form a verification task group under Chip Alliance. If you want to collaborate on this effort, let me know. So just contact us, and then we'll figure out how we can collaborate on this. Thank you. OK, so basically, from the trace, you know the branch is hit or not. Because after you run the program, you know the operand value of the branch instruction. You know it's hit or not, right? So in a sense that we get a series of branch instructions, we know it's hit, hit, miss, hit, hit, miss. We don't actually care, or we don't actually put assumption how you actually implement your branch prediction. We're just presenting a problem for you. Like, we create different scenarios. It's back-to-back hit, back-to-back miss, and hit and miss combined. We make sure you cover that, and we make sure our actual instruction generator can give you that. Okay, the question is about hazard condition coverage. So it's the same way. So because you know your kind of the sequence of instruction from the trace, and you know what kind of operand you are looking kind of using for every instruction. So you know back-to-back instructions, there are some dependencies, whatever read after write, write after write, this kind of a thing. We can actually get from the trace because we actually run the simulation with ISS, so we know the result of the instruction. So we know the values and the different operands, whatever. So we can define that, okay, if you're the later instruction using the output of the previous instruction, you have a hazard condition you have to hold until. Right now, at this point, it's kind of adjacent instructions. We can actually extend that to kind of have a window, like 5 instruction window to see. So understand, because if you have a more complex pipeline, you care about more kind of a, yeah. Now, one last question. I think you're talking about the configuration of different flows, right? Yeah, how do we set up that thing? So essentially, the information is the same, because basically information is a subset of RISC-V spec you support, right? So you just need to define that format in some way. Then, because different flows still have different way, like an input. IISS will have the own input configuration file format, and instruction generator take different type of format. You just need to do a conversion. As long as the source is just single source information, then you can convert to different format to configure different flow. So basically, you need some conversion to make it happen. Okay, I can take Mark question offline. I will be around. So thank you.